let's explore operators and eigenvalues. That is, we want to develop the mathematical rules for performing quantum mechanical calculations. Now, everything in quantum mechanics pretty much is derived from the time-independent Schrödinger equation. The Schrödinger equation allows us to determine the wave functions of the system. We're interested in those because they provide a complete description of the system. And the way we find them is by applying the Hamiltonian operator, this h hat, to the wave function, which represents an eigenfunction of the system, and it returns an eigenvalue, the energy, times that wave function. So just a constant times the wave function. Now we want to pose and answer the questions: how do we derive these operators, and how do we use them? So let's take it back to the postulates of quantum mechanics. Postulate 3, collapse axiom A, states that each physically observable quantity is represented by a unique operator that acts on the wave function. Operators that correspond to physical properties must be linear and Hermitian. Therefore, the wave functions that describe the system must be orthogonal. Let's see what a few of the implications of that are. Second, postulate 4 states that a wave function psi forms an eigenvalue equation with the operator a hat, such that a hat operating on psi equals a constant alpha times that wave function psi. Alpha is the value of the physical quantity represented by operator a hat that would be measured experimentally. Any system whose wave function is an eigenfunction of a hat has a definite value, alpha. The time-independent Schrödinger equation, remember, contains essentially all of physics and chemistry if we can understand the Hamiltonian and find those wave functions. Well, that sounds like everything's solved, but it's not quite that easy. First of all, we need the operators. We'll have to figure out how to find these, right? Operators are just mathematical manipulations that we're going to do to the wave function psi. The Schrödinger equation itself is an eigenvalue equation. That is, the operator operates on psi, the wave function, and it returns an eigenvalue, the energy, if our operator was the Hamiltonian. To find the energy, and since the total energy is such an important thing, we give it a special name. The Hamiltonian is the total energy operator, right? We need to develop the right mathematical machinery to find the energy, right? The Hamiltonian is a second-order differential operator. That is, it contains terms like the second derivative with respect to a coordinate squared, but it doesn't have higher derivatives. Its form depends on the system. There's always a kinetic energy term that looks pretty much the same, but it's the potential energy term that contains all of the interactions. And we've got to consider all the interactions in the system to put together a proper potential energy term and construct our Hamiltonian. So what we need is one known system. One system that we know all the energies very well. And the hydrogen atom provided this system. We know its energy level structure from spectroscopy. So then we should be able to solve the Schrödinger equation, and we only need to solve it once. And that will give us the wave functions that describe all the states of the hydrogen atom. Once we have the wave functions, we can now find the other operators. There are other values, linear momentum, or angular momentum, rotational momentum, spin, all of these other known or values that we can measure and get values for. Once we have the wave functions of the system psi, there's one set of wave functions. So if we know the values of other measurable, observable quantities, and we know the wave functions, then we can construct the set of operators that lead to these values. We can do that all for the hydrogen atom, and then the wave functions are system specific. Each atom has its own set of wave functions, but the operators are universal. So once we've determined the operators from the hydrogen atom, we can use them for all other systems. Then we can measure their energy level structure, solve the Schrödinger equation, get the Hamiltonian for that system, and then apply the known operators to the wave functions we found to find all other experimentally observable properties of that system. So, how do we work with operators? Well, let's introduce that notation. You've seen it, but let's just make it explicit, right? We want to differentiate operators from scalars from vectors. And we do that with a notation where we'll put a little circumflex on top of a letter. We'll read that p hat. That is the linear momentum operator. And that's how we differentiate an operator from a scalar. A scalar is just in italics, right? Whereas a vector quantity is boldface in italics, right? First rule of working with operators is that the order of operation is important. First operate, then solve the resulting equation, right? The order of operation is indicated by how we write things out, right? So if we have a system that looks like this, we've got our wave function, we always move across this way. So if we have this written down, we're first going to take the derivative with respect to x, then we'll multiply by x. Whereas written this way, first multiply by x, and the result that you get, take the derivative with respect to x on that. Next, operators operate on functions, not other operators. So when we have two operations in a row, such as listed here, first B operates on psi, then A will operate on the result that we got from B operating on psi. Operators may or may not commute, right? The order of operation is important, and therefore we have to check for each set of operators that we've got. It might seem obvious that if you operate first on psi with B and then A, that it should give you the same answer as if you did A first. But that's not always true. There are some systems where that's true and some where it's not true. And so if it works, if these two are equal, we'll say those operators commute. If it doesn't work, if order of operation is important and these two do not give the same answer, then those operators do not commute, right? So we've developed what we call the commutator. It's given this symbol here, the square brackets A hat comma B within square brackets, and it means that we're going to take the difference between B acting first and then A, and then we subtract off A acting first, then B. When this has a non-zero value, the operators do not commute. When the commutator is equal to 0, the operators do commute, right? This is going to be important later when we get to uncertainty relationships. And if it helps, you can put the wave function in here directly to remind yourself that B is operating first on the wave function, then A, and we subtract off A operating first, then B. Operators act on functions to produce new functions. So postulate 3 said the operators were linear. If they're linear, then what that means is if we have A operating on the sum of wave functions, then that's equal to A operating on each one of those, and then we sum up the results. Likewise, if we multiply by a constant, you don't have to worry about order of operation when you multiply or divide by a constant, right? You can just factor out that C, pull it out of there, and let A work on the wave function. Finally, postulate 3 also said that our operators are Hermitian. Hermitian operators, what's important about that is Hermitian operators give real eigenvalues, and they correspond to real observables. Things that we can actually measure in the lab are all going to be real numbers, right? So finally, summing up our discussion here of operators and eigenvalues, right? Everything is derived from the time-independent Schrödinger equation. We've got that Hamiltonian operator operating on a wave function to give us the energy times the wave function. The wave function is found by solving this time-independent Schrödinger equation. The wave function contains everything that we can know about a system. From a system with known eigenvalues, like the hydrogen atom, we can derive expressions for all the operators, and these expressions are universal. So then we can apply them to all other atoms to find their wave functions, right? And the order of operation is important. Not all operators commute, right? The commutator, which we have down here, is non-zero for some operators, and then we'll find that they don't have, if this is equal to 0, then they don't have an uncertainty relationship. But for some operators that don't commute, where this commutator has a non-zero value, then those operators will experience an uncertainty relationship.